Hello, hello, hello. Welcome, people, towards our new CodamX session. Just a kind reminder for people from home as well. CodamX are actually sessions where we are supposed to inspire you about cool technologies or cool projects that some of the developers are working out there. Okay? Today we're going to talk about assembly to WebAssembly, compiler's writer's tale. So it's all about compiler optimization and visualization. But to be honest, like people that know me from Codam, what do I know about it? That's why we have a fantastic speaker, Alessandro, who's the founder and CTO of Leaning Technology, who actually wants to share with you a cool project that he worked on. Let's give a round of applause to Alessandro. And one more thing before we actually kickstart administrative stuff. This is going to be an intense session, pretty technical. That's why we actually prepared Slido for you to actually ask your questions. So especially for the people from home, whenever you have a question, go to slido.com, #CodamX, and include your questions over there, because Alessandro will actually take those questions at the end. The people from the audience, I would also suggest that you do it throughout the talk so that you don't have to memorize it until the end, okay? Because the talk will be pretty technical. So we are actually facilitated this Slido for you to keep track of your questions. Okay? Take the stage, Alessandro.
Thanks, Victoria. Good afternoon, everybody. And it's a pleasure being here today to show you a little bit of what we do. And thanks to Codam for giving us the opportunity to actually being here today and express a little bit of how our techs are actually built. My name is Alessandro Pignotti, and I am founder and CTO of Leaning Technologies. I was born and raised in Rome. I moved to Pisa for my studies during university, and during that time, I also had the opportunity of spending several months in the US, and this was pretty important for me, give me more perspective on, especially on what would eventually make me build a company from scratch. And I've been living in Amsterdam since 2014, so I've been a proud Amsterdamer for 8 years at this point. It's pretty nice. Leaning Technologies, the company we founded, was founded in 2012, which means that this year is actually the 10th anniversary of our company. It's a pretty good goal to reach, especially because we as a company are actually bootstrapped. So we have never took any external funding, and we always pretty much lived with the money we made by selling things that people need and use. And these things, there are 3 main products that we work on. The first one, in chronological order, is called Cheerp, and it's a C++ to WebAssembly and JavaScript compiler. The second product we made, using both the experience and the tool itself that we built for C++, is CheerpX, which is it's used to convert to Java and make it run in the browser using JavaScript and HTML5 and WebAssembly, but it would be not probably correct to call it a compiler, since due to the nature of Java is more similar to a full JVM. And the latest thing we've been working on is CheerpX, which is the main topic of the talk today, and which is x86 virtualization technology built using WebAssembly. And what we do pretty much is we find different ways of running existing applications in the browser. And to some people, this may appear to be something impossible. I remember pretty well that when we first released CheerpX, there were people on Reddit telling us that this is clearly a fraud. It's impossible to run a graphical Java application in the browser. It's not something that can be done. And I found this pretty surprising, since actually it's a core result of computer science that most modern programming languages are Turing complete, and all Turing machines are equivalent, which means that it is mathematically demonstrated that we can always run anything on anything. The difficult part is making this application run fast. And I think that one reason why it may appear to be an impossible task to run an arbitrary application in the browser is that because the problem when you look at that altogether, it may seem daunting. And something we do as engineers is try to split up a very big problem into smaller ones that we can deal with. So it can be useful to actually see an application as layers of code. At the top layer, we have the application logic itself, which is most usually the part that is most interesting to people. So let's say that, for example, you have a painting application, you have Photoshop. What you care about is the logic for the brushes, for the float fill, for filtering, these sort of things. If instead you're doing a word processor, you care about justification, spell checking, whatever. It's a completely different set of things, but it's what in the end matters to the user. But all these applications are eventually built using existing libraries or frameworks, and usually below these libraries or frameworks, there is the operating system itself, and below there is the hardware. And what is interesting is that for each one of these layers, when we do our porting, we are not necessarily forced to use a single approach. We can mix and choose and use different solutions and use the one that works best in every single case. For example, we can decide to compile something. Let's say that we have, for example, the source code of the application, like we do, for example, with Chirp. We can take the code, we compile it to WebAssembly and JavaScript, which is something that can then run natively in the browser for best performance. We can also decide to simply re-implement something from scratch instead of trying to compile it, run it as it is. For example, if you're doing a port of a game to the browser, you don't really care about porting the OpenGL library from the system. You can directly use the WebGL implementation that the browser provides. And another option, again, is to emulate. So in this case, maybe you don't have the source code, and you simply take the existing representation of an application and you run it step by step. And this is what we do with CheerpX, for example, but in a sense, you could also argue that this is what happens with Java, although the situation with Java is a little bit more mixed. It's somewhere in between. And it's also interesting that pretty much, if you look at this hierarchy of layers and you stop at various points, you get different approaches to porting. Now, traditionally, if you had a desktop application and you wanted to make a web version of this application, your only choice was pretty much just to rewrite it from scratch. So you will take the logic you care about. For example, when Google wanted to make Google Docs, they started from scratch and made a new word processor with the feature that people care about, but without using any of the existing code of existing word processors. This is something you can always do, but it's not something that we advise because it's horribly time consuming. And you will also create many, many bugs that you will need years to solve. It's very expensive, pretty much. A better solution is to take the application logic and compile it. And this is something that we as Leaning Tech have been doing a lot early in the history of our company, where we will get commissions to port games to the web. And the way we will do this, we will keep the existing C++ code and all the parts of the game which are relevant. So pretty much the AI, the UX, the score assignment, all these sort of things will be contained into the application code in C++, and we will compile all of it. But for example, we will not compile OpenGL. We will use WebGL as it comes from the browser. And we can go even one level below and keep not only the application, but the whole library. And this is what we do, for example, in Java with CheerpJ. And the reason we do that is that fundamentally a Java application, even a small one, even a small hello world that just prints something on screen, will actually use hundreds and hundreds of classes from the Java runtime. This is just how Java works. This is sometimes surprising for our users that somehow have this idea that if they compile a small application, they don't need the runtime, but this is never how this actually works. You always use part of the runtime when dealing with Java. And if we go even one layer below, we see the approach we have done in CheerpX, where we take everything up to the system call level. So in the case of CheerpX, we take all the binary code coming from the full binary, all the libraries that this application use, but we stop at the level of the system code, which this means that in CheerpX, we don't actually run a Linux kernel. It means that we actually have implemented the Linux system code so that an application can run on top of that. And so I mentioned CheerpX. Let's go a little bit in depth about how this actually works. And so CheerpX is a technology to run unmodified, arbitrary x86 applications in a browser. And since day one, we designed it to be generic, robust, and scalable. And in this context, generic means that there should be no specific limitations on what sort of application you can run with CheerpX. There should be no special command line flags that you have to use when compiling the applications. There should be no special library you have to link. It should be able to deal with the applications as they come from your regular Linux distribution. It should be robust. And what this means is that we should deal with all the corner cases that you might think that you can avoid. For example, dealing with self-modifying code or with code that is generated at runtime. And the reason we have to do this, because to be useful, we need to be able to run things like Node.js that actually internally will generate code at runtime. So we cannot really trust that all the code that we execute existed at compile time. And it has to be scalable. What this means is that we did not want to make something that only works on your Hello World application. We wanted to make something that could work on real user interesting workloads. This means that we had to support multi-threading, multi-processing, hundreds of megabytes of memory consumed, and long-lived applications. In practical terms, CheerpX is a C++ application that we wrote from scratch. It's all our IP, and we compile it using Chirp. This is a regular pattern in our company where we use our own tools to make further tools which are more advanced. The system uses a two-tier execution engine. It will be possibly more correct to say that the tiers are three, but let's keep things simple if we can. And this is a pretty common architecture on modern execution engines for dynamic languages. You would see the same approaches used pretty much in the V8 engine used by Chrome or the JavaScript core engine used by WebKit and Safari. And we stop at system calls. This gives us some advantages, since, for example, when we can see that an application is trying to access a file, and we can decide to redirect this file to an HTTP backend or to another backend if we want to have it read-write. But the limitation we pay for these advantages is that we cannot run system-level code. This means that we cannot truly run the Linux kernel itself. We have to emulate it, and we cannot run Windows on top of this system because we cannot run the kernel. This is something that in the future we might change. We might implement this sort of support, but right now this is an effective limitation. So it's nice to talk about things, but I know that you guys are hands-on people. Maybe you want to see something. Okay, so this thing is webvm.io. It is a public demo of CheerpX that we have released a few months ago, and we keep updating over time. You can play with this if you want. It's public, and if you find any bugs, you're welcome to report them on GitHub. And Jules, who is in the audience, will deal with them eventually. And let's see what we can do with this thing. I'd like to prove to you that you can actually run arbitrary binaries that we have not seen before. Let's try it. So I'm going to open a new file, and I'm going to make a very simple hello world in C. And to make it something not necessarily completely trivial, let's return a failure. So instead of the usual return 0, let's return an error code and see what happens. We save this file, and now we will invoke GCC on it. Now, what's happening here in the background is that the data for the GCC application is being loaded from the disk backend and is being parsed in memory. The address space of this application is being populated, and the application is starting. And the way this works is that you start application from the entry point, and you just let the whole execution flow proceed. This thing is finished. Let's see if the application can run. It does. What is the error code? 42, which is what we expected. And you might still think that maybe there is a trick here. So you might have heard that it's possible to compile C++ to WebAssembly. We do it ourselves. Is this maybe a WebAssembly program? Let's see. We can ask the system. I can use the file utility and ask what is the type. Well, the system is telling us this is a 32-bit i36 application, which is what to expect. As further proof, let's see the code. This is what you will expect from a binary application. So to get back, what we've seen so far. We've seen that in the context of CheerpX, there can be multiple processes. The first process that starts is bash, which is what controls the terminal. And bash has spawned GCC. We could have even tried Python if you wanted to. And as these programs run, as these processes run, the two-tier execution engine of CheerpX will make them proceed. And the interpreter will keep running for code that is executed not very often, and eventually code that is hot enough will be compiled to WebAssembly and executed much faster as WebAssembly code. And eventually, these applications will reach some system call. For example, GCC needed to open the source file to see what was the content. And this is something that does not run in the execution engine, but is something that we implemented ourselves as part of our C++ code. And this is something that also communicates with the browser, because remember that this is still a browser, right? And eventually, we need some code that runs in JavaScript to be able to actually write things on screen. To have the console, the terminal, give us any information, we need eventually to create some JavaScript string from the bytes that came from the execution engine. Now, let's discuss a little bit about how the interpreter works. So on the left, there is a small test case that those sums those are print in the entry block of the main function. Then for loop starts, and these for loops will iterate a bunch of times, and 50% of the time will print a message, and the other 50% of the time will not. And remember that CheerpX is not able to see this code. This code is ours. What CheerpX will see is the binary code that you have on the central column. And truly, it will not even see that. This is a human-readable form of the same code. What CheerpX will see is just a bunch of bytes without structure, one after the other. And how can we reason about that? The reality is that reasoning on just this soup of instructions is pretty inefficient. So even for the small example we've seen so far, we have probably been running hundreds of millions, if not billions of instructions to compile that application with GCC. And you can easily imagine that trying to track metadata for every single instruction will be not something that can be done. So what we do is that we simplify the problem for us by trying to structure the problem into what we call the control flow graph. And the role of the interpreter is not only to execute the code for the first few times when it's not very hot, but it's also to build the control flow graph dynamically. So the interpreter will start the execution, will eventually figure out that code goes back into the loop, and will proceed conditionally either on one side or the other. And from this information, it will build these basic blocks, what we call. So a basic block is a sequence of instructions that terminates on a branch. And all the analysis and all the optimization and all the jitting we do is based on the representation that you see on the right. So on this control flow graph, not anymore on the original sequence of instruction without any structure. And what we can do for that, what we do is that for each block, we are able to maintain a counter. So we can count how many times this code is executed. Now, what do we need this counter? Well, the point is that we need to decide what to actually JIT compile. And you might argue, why don't we simply JIT compile everything, since it runs faster? Well, the issue with this is that compiling something is also overhead. So in a sense, what you're doing is that you're making an investment. You're investing some time, hoping that the time you save in the future will pay back that with more. So what you're looking for is literally return on investment for time spent. And in an ideal world, we will be able to know how many times a piece of code is going to be executed in the future. But this is not something we can actually know. We are not able to see the future, so we need to somehow settle for the second best thing, which is that to use the past information about how many executions we've seen to predict the future. So what we do is that if we see that something has been executed only once, we will predict that it will never be executed again. If something has been executed 100 times, it's very likely that it's going to be executed another 100 times. And in the previous example, of course, the entry block is executed only once. The exit block is executed actually 0 times, since we are still in the loop. We need not even reach the exit yet. But the loop itself is going to be executed many, many times. And interestingly, the print block inside the loop is going to be executed half of the time of the loop itself. And eventually, one time we go back to the header of the loop, to the beginning of the loop, we will figure out that this code is actually pretty hot, and we want to compile it. And at this point, we generate a new function in WebAssembly that starts from the loop header and includes all the blocks which are sufficiently hot. So in this case, we would include the print block, but we will not include the exit block for 2 reasons, really. So on one side, this block is cold because it's not been executed many times, but it is indeed not even been executed. It's been executed 0 times, which means that we do not even have any information about that. We don't even know if when the code gets there at the exit block, if there is valid code or not. There may be a fault. The code may simply explode there. We do not know yet. So what happens is that in the JIT code, when we eventually reach the end of the loop and we need to exit from it, we go through what is called a bailout. So at this point, the JIT code will bail out, will go back into the interpreter, and the interpreter will have another opportunity of figuring out what is the structure of the code that follows. Because there may be anything. There may be a massive big function below, but we don't know it yet. The interpreter has to run at least once to figure it out. And so we have discussed that we have to deal with these billions of instructions. And how do they look like? Well, this is a pretty basic instructions. And as you can see, even a basic one looks fairly complex. And this is indeed in the name of the family of architecture that x86 is part of, which is called the complex instruction set computers. And we can actually see that this operation actually does a bunch of things. It will load the value from a register. Then it will load the value from memory. We'll do the actual arithmetic operation. And then it will also compute 6 different flags, which is pretty expensive. And it will also, again, store the result in memory. And it's interesting that this division into blocks is not just something we can do conceptually when I made a drawing about it. This is something that the CPU can do internally. The CPU does not really execute these instructions altogether, but splits them into what they're called micro operations. And what's interesting is that this division is made for internal purpose, so the CPU does that to optimize its own resources and its own pipeline. But from the point of view of us, the people that make this code, we cannot see it. We can only see the instruction as atomically committed after all that part has been done. Keep this in mind, because this idea that you can change things as far as nobody can see it is going to come back. And the flags actually are worth a little bit more discussion here, because in the case of the CPU, there are, again, 6 flags, and they are computed for free. They just come as a side effect of the actual electronics that compute these values. In the case of CheerpX, we don't have this privilege, because we can do the arithmetic in WebAssembly, sure, but nobody will give us the values of the flags. And if we have to compute them explicitly, it's going to be very, very expensive, and we like to avoid it as much as possible. And so the question is, how can we make these very messy instructions, billions of them, run efficiently? Well, we can do some optimizations, but to discuss about them, let's go one step back and try to see what even mean to do, what is the meaning of doing compiler optimization. This is a very simple example. So we have the TMP variable, which is assigned to the result of this expensive algorithm, a function call. And it doesn't really matter what this function does. We can pretend this something, maybe it's doing some integer factoring, whatever, something that takes a long time to, or relatively long time to run. And we can see that this variable is actually never used in this code. So the question becomes, can we simply remove the variable, remove the call, and make everything run fast? Well, we can if certain assumption holds. In particular, we need to assume that this expensive algorithm call has no side effects. Now, side effects is a terminology we compiler engineers like to use. What this means intuitively is that this function should not fiddle with anything that it should not touch. So it means that it should not write to global memory, it should not try to print something on the console, it should not try to write stuff to files, it should not do anything which can be seen by somebody else. If that's the case, if this function has no side effects, then there is a basic optimization which available in all compilers, which is called DCE, and that code elimination, and this the variable and the call will be removed, improving the performance of the program. Pretty easy. Let's go one step forward. In this case, we have a similar scenario, but in this case, now the variable TMP is obviously used. It's written there, it's used as the return value. Can we do something about that? Well, the idea is that DCE cannot solve the problem for us anymore, but we can try something different. We can use a class of optimizations, which is called IPO, which means interprocedural optimizations. What this thing do is they look at the program, at the whole program, and try to figure out, let's see, is it actually the case that this value is ever actually used? And it will look across all the code, we look for all the places that call this function, called the func1 function. And if nobody is actually using the return value, because maybe it's simply dropped, that is never stored in any variable, there are 2 transformations that we can do. First of all, we will convert the function to void, and then we can remove the return statement, making TMP unused, and we can remove the whole thing again. This is to show you, the sample shows you that something is used really depends on the context you're looking at. It may be not as trivial as it sounds. The third and last example, we do something even more complicated. We actually have the usual situations before, but then we compute a derived value. So from TMP, we compute a value called TMP2, which only uses the least significant 16-bit of the value. And then we compare these values against 0, and we return true if the value is negative, and otherwise we return false. Well, let's say in this case that IPO cannot help us. So the interprocedural optimization cannot easily tell us that we can simply drop the whole thing because nobody uses it. Somebody is using this result. What a sufficiently smart compiler could do, which is a mythical creature that does not exist in practice, but we like to talk about that, is that it can notice that in the end, the value of the result only actually depends on the most significant bit, on the top bit of TMP2, which we know that is 0. So we actually know that the return value is false. We know if we do this transformation, then TMP2 becomes unused, and TMP becomes unused itself, and then we can remove the whole thing one more time. The idea here is that I wanted to pass you is that it doesn't really matter if something is used. What matters if something is observable. So is a computation actually seen by anybody? Can it have any impact on anything else? And if it doesn't, we can simply kill the whole thing. And this is actually a lens that you can use to actually see many, if not most, of the optimizations that both compilers and CPU do. As far as nobody can see that you've messed up with how the code runs, you are free to do whatever you want. How this is useful for us? Well, for example, we can go back to the previous example, and we can remember that we are never dealing with an isolated instruction. We are dealing always with many of them, and they come in blocks one after the other. So we can use this structure to try and optimize things away. So for example, in this case, we have XOR that changes the value of the register X, and then this register is used one more time for the same operation as before. And we can notice that the flags are computed by the first instruction and then immediately overwritten by the second one. And this means that we can actually completely drop the first computation. It's going to be overwritten. Nobody's reading them in the meantime. Nobody will notice. And again, there is also something else we can do. Since the first instruction is modifying the same value that is used by the second one, we can avoid the load of this from the context. We can simply use the result as being just computed. And of course, guys, this is just a quick overview of the sort of things you can do. You need to imagine that there are many tricks that you can do, trying to exploit the structure of many structures that come after the other. But don't follow this idea. We can fiddle with execution, make stuff run fast, as far as nobody looks at the result. Now, what it even means to measure performance? The issue here is that ideally what you want to do is to measure time on your watch. So you want that something runs faster in the world clock time, as we say, so in real world time. Working with that is actually pretty tricky, especially in a system which is dynamic like CheerpX, because remember that we are dealing with real applications that are multiple threads. Each one of them will bring some noise around. And the system itself is actually completely dynamic and asynchronous, since we generate WebAssembly code when some conditions are reached, and then we ask the browser to compile it, and the browser will eventually execute a callback that tells us that the code is ready. So we don't have complete control on the timing. And these sort of things introduce lots of noise, which makes it actually pretty tricky to optimize something just by looking at the time. So we do something different. We actually look at what we call the instruction multiplier. Because if you think about it, what we're doing is that we're taking some x86 code, we are converting it to WebAssembly, and then the browser will itself convert this code one more time to native instructions. Now, the native host of the browser is not necessarily x86. It may be, for example, a Chromebook. It may be a phone. It may be something ARM-based. And this will still work. So CheerpX will still work on architecture which are not x86. It's fine. But for the purpose of optimizations, we do consider the common case of having a host which is itself x86. And then we can ask the question, how many instructions do we generate for each original instruction? And this is what we call the instruction multiplier. So what we have right now is that we are around the 5x multiplier on average, which is also sort of consistent with what we observe when we measure work clock time, which means that it's a good proxy measure. It's a measure that guides us in the right direction while being simpler to reason about. Of course, this depends on the application. So we have some lucky applications that maybe can execute with a 3 or 4x slowdown compared to native. There are some unlucky applications that maybe run with 10x slowdown compared to native. And in that case, it means that we need to work on them a little bit to make them run faster. And it's also interesting that to even get to the point of reasoning about this stuff, we had to develop some custom tooling. Since you may imagine that we could simplify up the Chrome developer tools, click on performance, and get some result from there. This is actually not the case, mostly because the Chrome is not able to deal, the provider of Chrome actually is not able to deal with dynamically generated code. So the fact that we are keep generating new code at runtime and destroying old code that is not used anymore seriously confused the provider. And there is also the issue that even just opening the dev tools significantly slow down the performance of the whole thing, which means that you're fiddling with the same thing that you're supposed to measure, which is pretty bad in general when trying to use the scientific method to improve something. And what we've done in the end is that we have used the same building blocks that the Chrome dev tools use at the lower level to try and get some solid information, and then we post-process ourselves to get something we can analyze. And I'd actually like to show you what I mean by that. I have another, not a demo, but I have an output I'd like to show you. And it should be here. So the thing you're looking at is the output that CheerpX generates from an original function that is actually come from the Adobe Flash Player plugin. One of the products that we actually sell is a system to run the legacy plugin that is not supported anymore safely on modern browsers by emulating it across CheerpX. And this is a pretty big function. It was originally 850 something instructions long. and it will become something which is 3,000 instruction long or so, with a multiplier around 4. So this is actually below average, which sort of makes sense since it's something that we've been working on to improve. I've been working personally on this for several weeks. And I'd like also to show you how this ratio works for different blocks. If I go down, I should be able to show you that, for example, this block here, I can highlight it for you, maybe it's better, as some multiplier of 4. This one is 2.8, 2.6, 6.2. This one is pretty bad, for example. This one has a multiplier of 10.5. And we can see this is actually a call. And calls are pretty difficult to optimize, really. But I already have some ideas about something we can do that, mostly by taking advantage of extensions of the WebAssembly standard that would make it possible to remove some of the extra checks here to get to a better result. What is the objective that we want to reach eventually? So as you can see, it's fairly within reach to reach a 4x multiplier. And I think that in the future, with enough work, we'll probably reach a 3x multiplier. Getting below that, it's always possible. It's going to be more and more difficult over time. And usually, when trying to reduce this, there is actually a multi-side approach. On one side, we can improve CheerpX itself. We can figure out new optimizations. We can figure out new way of generating code. The other things we can do is to actually work on the WebAssembly standard itself. We actually contribute to the standardization to add some features that will be useful for us. And for example, in this day, Tom, that is also in the audience, is working on implementing an extension to the standard, to adding it to the Safari implementation of the engine so that we can push it forward in the standardization process. And something else we can do is to actually improve the engines themselves. The output I show you actually is the output generated by Chrome. And these days, I'm actually also personally working on improving the Chrome code generation by freeing up one of the registers which are currently reserved. So something you might be aware or not is that the x86 architecture is pretty register starved. What this means is that there are not many registers, and registers are fundamental to achieve high performance of code. And so if there is a reserved register which cannot be used by user code, that's pretty bad, because it means that you're probably leaving quite a bit of performance on the table. And what's interesting is that both contributing back to V8 or to the engines in general and contributing to the WebAssembly standard is something that has actually not just a technical component, because of course you need to do something which is itself pretty difficult. There's also the engineering component, which means that you need to be able to sort of make this change or this proposal you're building something that people can reason about and understand and eventually approve. There's also the political issue and the human issue, because you need somehow convince people that have other priorities and they're working on other things, that they have their own life, that the stuff you're working on is actually important. And it's often the case that that part is the most difficult of the three. Now, if we actually reach the 4x multiplier or the 3x multiplier, would that mean that all applications we run with a 4x work clock slow down? That's of course never the case. There is always something that can go wrong. In particular, it may be that the JIT compiler might fail. So maybe that there is some code which is ugly enough that the JIT compiler cannot reason over that, and it gives up. In that case, the code will run in an interpreter, which is pretty bad. And so if we see an application that behaves not great, the first thing we should look at is to make sure that all the code runs in the JIT as much as possible. It may also be that the application is using some types of instructions which are not well optimized. In particular, the legacy x87 FPU, so the 80-bit floating point values, are pretty tricky to get right. We already do a few miracles there, but it's something that always requires some additional work. And then there is the issue of vector instructions. Now, in WebAssembly, there is actual support for vector instructions, CMD, but we don't currently use it. It's something that we need to expand in the future. So this means that right now, if an application uses a lot vectors instruction from x86, we pay a significant slowdown, maybe a 2 for X slowdown for that specific part of code. But it might even be that the application goes slow not because the code is not of sufficient quality, but because there are other overheads. For example, it may be that the JIT compiler itself is taking too much time. Remember that JITting is an investment. You need to make good investment decisions there. So it may be that we need to fiddle with the heuristics that we use to decide when to compile something, or it might be that we simply need to optimize the JIT compiler itself so that it does not consume as much time. Or it may simply be that the application is actually waiting for data to come over the network, because don't forget that CheerpX Web VM, there are still web apps. So they are still dealing with the normal stuff you have to deal with when doing very big web apps. And this is a completely different engineering domain. You need to do your usual preloading, usual caching, using CDNs, these sort of techniques. My goal personally is that if we reach the point where we can run consistently for most applications with a 3 or 4x slowdown compared to native, I will be pretty happy about that. And pretty much, I think that's it. If for any reason you found the stuff that we work on interesting, please apply for an internship position at Leaning Tech. We've been very happy with the quality of the students we've seen so far, and we like to keep this relationship going in the future. Thank you.
Let's give a round of applause. Let's give a round of applause to Alessandro. Thank you so much for going into depth. To me, it was in depth. You name it, guys. Let's kick off the Q&A session,
Sure.
because I bet, the guys have a couple of questions to you. By the way, we are here to learn, okay? So there is no such thing as stupid question. That's the deal, okay? People from home as well, please, ask your questions. Go to slido.com, hashtag CodamX, the big C and big X, and write your question inside there. But in order to give them a little bit of time to think, to formulate their questions, I thought to kickstart the questions with your two colleagues, Jules and Tom. Jules and Tom have been with Codam before, right? And now they are working together with Alessandro in Leaning Technologies. And I would like to kickstart with you guys. Can you explain to us, right, why do you like this technology, and especially if you consider, your experience with Codam, right? So maybe you can relate how, this project relates to what you learned from Codam. Sounds like a plan? Do I understand the question?
I was not aware of this trap. Don't look at me.
I'm improvising because I'm giving them just a little bit of extra time to actually fill in the... You can take my microphone, by the way.
Inspired, or should I start? Well, in Codam, we always start from scratch in a way. So we start from a problem from the bottom, and then we understand some basic concepts that we might not be knowledgeable with. And with Leaning Tech, it's a bit like that because you virtualize something, so you always have to look at what you need to virtualize and be able to reproduce it, be able to understand it at its very core, or it's always different, but yeah. So yeah, that's a bit in the continuation of Codam for me, and that's what interests me. And also it's nice to be surrounded with very knowledgeable people. And I'll give the mic to...
Yeah, I think when it comes to working at Leaning Tech, maybe the biggest advantage of being a Codam student is that we learn to, you're given a problem and you have to solve it, and you get some assistance from others when you ask for it, but you just have to dive into it, fail 1,000 times, and eventually get to something, and that's pretty much what it's like to be a Codam student. So it really isn't all that different.
Does this work actually? No? Okay, now it's working. Because I still have one question. So as a junior developer, right, would you actually use like CheerpX, and how would you use it? In which cases? I'm just curious myself, because what are the applications of it, right?
Well, actually, I have to thank my friend here, Dustin, because just before I ran into him, and I told him a bit about what we do. And he said, oh, I've always wanted to show my mini RT or my Cube 3D, which is a ray tracing project or raycasting project. And that's one of the use case we reach for, which is implementing a graphical server on top of the virtual machine and be able to run graphical projects. And for Codam, for example, either of going through the thing of compiling your whole thing and stuff like that, you just show it in the browser, you share a link, and people can see it, interact with it. Of course, it's complicated, but that's the kind of use I would have to be able to get rid of all the native stuff that you don't need in the end when you want to show something quickly.
Makes sense, huh? No, it's really clear to me, at least. Thank you, guys, sorry. I see already a couple of questions over there, but I would like, before I read those ones, I would like to take one question in the audience. Who would like to kickstart? Yeah.
If WebAssembly had like exactly the instructions you wanted, what would be the limits to getting this multiplier down? Like,
oh yeah, sure. So in the ideal world, let's say that we had all the instruction we wanted. I think if we, in that scenario, we could get pretty close to probably even less than 2, really. So if we can, I mean, but I guess the question is a bit flexible, the answer here, right? Because, okay, you say you can have whatever you want, but of course there is the issue that this whatever I want it to be somehow accepted by the whole web development community, which means I might not have everything I want. But let's say in the perfect world where we could control the whole thing, the whole stack, it is totally possible to reach possibly down to less than 2 is probably quite doable, yeah.
what would you be limited still by to not get it down to 1?
Well, the limit of sandboxing mostly. So this actually connects to another question I see on the screen. So there is still the issue that you need to run inside an environment which is isolated from the rest of the machine. You don't want your code to be able to fiddle with the system. And this thing, in one way or another, will come with a cost. So the cost of WebAssembly itself is actually pretty low. There are some tricks that allow that. A trick, for example, is that currently WebAssembly lets you only to use 32-bit address space, okay? While most physical machines are actually 64-bit. And it's pretty funny that there exists a proposal for a 64-bit wide WebAssembly, which fundamentally is not really practical, because one of the advantages of having a small address space in a big one is that you can do memory isolation extremely cheaply. But if you had a wide address space, you will lose that. You will need to pay for every single memory access. So it's, you know, for this security and this efficient form of security comes with a price.
Anybody else? Otherwise, I take one of the questions from the...
Yeah, so one of the things is you obviously want to bring the compile time down for everything you want to convert to WebAssembly, but you also want to make sure your program is fast enough to be usable. So do you have the option to like shift that balance? So for example, if I want to show my ray tracer, I want to make sure it's fast, and I don't really care if I have to wait, like if I have to tell my mother like, oh, just wait half an hour and I can show it in the browser, you know? So in that case, I don't really care how long it takes to compile, but in some other cases, I may just only care about compile time and not really about runtime.
This is a fair question. So in a sense, what you can fiddle with are these thresholds, these numbers that we have to reach before we start compilation. And these are indeed just numbers which are actually sort of arbitrary. We just decide to settle with that. Yeah, a few hundred seems to work fine. Let's use that. And of course, you can tune them. There is currently no such option, but in general, I think it's pretty true that in the end, you will truly not notice the difference, because in reality, you start compiling that again when you reach a few hundreds of execution, and you reach them very, very fast. So it's not like you will start compiling after a couple of minutes that things run. Actually, the system is structured so that code that is unused for 1 minute is dropped. Because otherwise, this thing, again, has to be scalable. It has to work on real applications for half an hour. And so if you don't do recycling, and if you don't drop things which are unused, eventually you will explode. So the system needs to take into account also to run things for long, you need to also eventually drop things away.
Thanks.
Thank you.
I want to take one of the questions from the people from home. Primoz asks, when you compile programs, they use OpenGL. How to make sure that the API call to WebGL will behave the same as the OpenGL counterpart?
Well, that's a funny question. So first of all, this question should actually apply not when you compile, but when you will compile. Or maybe it's actually not about CheerpX, but Cheerp itself, right? So no, this is something that then can be done already today. Well, the question, I guess, fundamentally depends on how much you trust the implementation of OpenGL and WebGL, right? So these two things are both standardized. And of course, there is also always the reality that what the standard says and what the implementation says and do are not necessarily completely aligned. But in the end, this is not just true between OpenGL and WebGL, this is true between various OpenGL implementations. So in a sense, even when you run something on your Linux machine and then you compile it using OpenGL to run it on your phone, it can be hit or miss if the thing actually works in exactly the same way. And the same applies to WebGL, but because fundamentally also WebGL is not truly a thing. WebGL is just an API that the browser uses that will let you access the underlying OpenGL implementation of the platform itself. which means that actually, if you run your application natively with OpenGL on the same machine as the application, as the converted web app, you will probably see that they run identical or probably very close to each other. But if you run on different platforms, you just have the usual problems you get when you cannot fundamentally trust that the vendor of OpenGL has done his job properly. It's a problem that we cannot resolve. It's outside the scope of what we do.
Thank you. Do we have one more question from the audience? Otherwise, yeah, we have one here.
What actually will happen if it runs like an AVX 512 instruction? What would happen?
Right now?
Yeah.
Right now, we get actually undefined instruction exception, and the thing will stop. Can we implement them? Sure, we scalarize them. So instead of in the particular case of IVX 512, there is not even truly a counterparty WebAssembly, because WebAssembly has SIMD standardized, but only up to 128 bits, which means that to run anything which is longer, we need necessarily to, in a form or another, scalarize it or still split up into smaller units. But still, you can always emulate them. So this is always possible. It's not done right now just because it's not a use case that we found so far, but it can be done.
Cool.
One more question from the people in the audience, at home, sorry. Can WebAssembly be insecure in terms of bare metal communication?
This is a beautiful question. And this is actually something that in my original plan, I wanted to speak about the security of WebAssembly, but fundamentally, not everything can stay in 45 minutes of presentation. And this is also a very common question that we receive from people on Reddit whenever we publish something. So something to keep in mind is that there is the feeling, I think, that WebAssembly can do more things, or special things that the browser would not otherwise be able to do. But this is fundamentally false. Actually, WebAssembly by itself cannot do much. So WebAssembly in isolation is just a piece of memory and some variables that you can manipulate and functions that contains the code. You cannot even do an hello world. You cannot print anything, not on the page, not on your console, not on anywhere, without the help of what we call imports. So WebAssembly imports in the context of the browser are pretty much JavaScript functions that you give to WebAssembly, and that these functions let WebAssembly actually use the browser. So this is the only way you can actually use to print something on the screen, to draw stuff on the canvas, to add elements to the DOM. The only solution is to use these sort of JavaScript bridges. This means that actually a WebAssembly program can never do more than what JavaScript can do, fundamentally, because all the access to the platform comes via JavaScript. And WebAssembly itself is absolutely isolated into this sandbox. So I remember that when we first released CheerpX, there were people that, for any reason, they found some sort of bugs and the tab crashed. This can happen, but what these people imagine is that they have found a security bug. This is never the case. You can never punch a hole in the security of the system by using CheerpX because it's an isolated environment. And it's also funny that we often have this sort of question also about with our work with Java. So one thing that we do is free Chrome extension, free for non-commercial use, that is called the CheerpJ applet runner, which is a one-click thingy. You can install, you click, and your legacy Java applets now run into modern browsers. This may seem pretty useless, but we have 70,000 users, so we know that there are people in the world that still need these sort of things. And when we released that, people freaked out on Reddit, since they said that now you could have all the vulnerabilities of Java again on modern browsers, but you cannot, because this thing runs inside the browser. And indeed, this also comes with some sort of misunderstanding with people, since pretty much you run your thing, you start your thing, the applets run exactly visually identical to what you used to get before. And so people expect that the behavior will be identical too. So they expect that if they say open file, they will be able to select file on their desktop, but they cannot, because the system is virtualized. You can only access files which are contained in the virtual file system. And this is often pretty confusing for people, and I always find it funny that at the same time people are worried about security but cannot see that the file system is virtualized and you cannot access the system. Of course, you cannot have the two things at the same time. Either you are insecure and you access the system resources, or you are secure and you don't.
Are there more questions in the room? Yes, Harm.
So the standard library uses a lot of the vector instructions optimizations, but also a lot of annotations for cold and hot code and all that stuff. Is any of that also used, or do you just like detect the vector instructions maybe, or do you just discard them completely?
So usually, as far as I understand, your basic C library will do some runtime detection of what are the features of the processor to select various implementations for your mem copies, mem set, these sort of very low-level routines. And when you run under CheerpX, in the end, the exact same thing will happen because we do implement the CPU ID instruction. And the C library will start, will query CPU ID and ask what are the features on this CPU. And we will tell them, well, we support SSE, we support a bunch of things, and the corresponding implementation will be selected internally by library. So again, this is not that we have to pass special compiler flags as a special build to the library. We really want to work with whatever comes from the distribution. What you've seen so far in the webvm.io demo, it's the literal binaries that come from Debian Buster. They are the same binaries. We have not changed them in any way.
But I was more talking about, you say you support the SIMD extensions, for example. So one that would be like PCMP STRI, which would be significantly faster for searching for characters and strings. But would you then also just say, hey, we might have a faster implementation by just iterating over it byte by byte?
So I see your point that you might argue why you tell that you support these instructions while it's not true, fundamentally, because we run them, but we cannot support them as vector instructions. Well, the answer to that is that many applications just refuse to work if you don't support these instructions. So you need to deal with what you have. The right solution, of course, is eventually to just figure out ways to integrate WebAssembly, SIMD into our code generation so that we can get up to speed with that. It's not really a philosophical problem. It can be done. It's just a matter of putting the engineering resource to do so. Does that make sense? Was that the question? Yeah. Okay, thank you.
More questions? Yes, Christy, and then Saladin. Don't be too shy, you know.
Well, the thing is, I wanted to ask, so the WebAssembly, yeah, you can create binary. Sorry. Do you think that there is a division because of the job, like the whole web dev community and the, let's say, backend community, the software dev community, because yeah, the well, C and C++ is statically typed, and the JavaScript is dynamic. And do you think that maybe because yeah, these languages C, C++ are statically typed, like it might not be that inviting for the JavaScript developers to come into this? Or
so this is something that is more connected to, I think, how WebAssembly itself was first standardized and then actually marketed. I can see that there is an incredible level of confusion about WebAssembly actually is, what is intended to be. I will actually be speaking on the 16th of June later this year at the GS Nation conference here in Amsterdam. And I will be talking about, again, CheerpX and WebAssembly and these topics. And I am actually pretty curious to see how the audience will react, because it will be an actual JavaScript audience, which is very different from what we usually deal with. But what I think is that this confusion will eventually give way. So it will take some time for people to actually understand what is the role of WebAssembly. But whenever you find an article online that says stuff like WebAssembly is replacing JavaScript, or people that write articles like I rewrote my thing in WebAssembly and now it's 400 times faster. When you see these sort of things, really be aware that people have no idea what they're talking about. So there is really an issue of getting to know a technology which is still pretty new. The way I see WebAssembly is that it's sort of a computational coprocessor to JavaScript. So when you want to quickly work on your UI and your interface, I think it's still a good call to do it in JavaScript if you have that expertise. Myself, I'm not a JavaScript programmer. I will still do everything in C++. Whenever I do something that runs in the browser, I compile it from C++. It's just my problem, so this is not, I think, how people should work. But if you find out that you need something to run consistently in a fast way, or if you're doing a game, I think you should really do it in WebAssembly. And fundamentally, do it in WebAssembly really means doing it in some other statically typed language and compile it to WebAssembly. You never write WebAssembly manually. Well, you can write also the regular assembly manually. This is still something I would not advise to do.
I'd like to ask about
scaling, how it basically is performed, because like the presentation showed that there are some shortcuts. We divide it into layers. And for example, I don't know, there will be some sort of, let's say, graphical application, something which is, I don't know, vector space, whatever. And but the application also in next stage is more, I would say, classical. Does this mean that, for example, this graphical part is performed on some, I don't know, high GPU server, and for example, the rest is on other, some sort of, I don't know, classical resources like, I don't know, just CPU server?
Okay, right. If I understood the question correctly, what you're asking is that since we said that we are splitting these applications logically in multiple layers and we can decide how to run them, maybe we can run them on some even external resource or something computationally very efficient. And the answer is certainly yes, but if you think about it, this is what already normally happens whenever you run a graphical application that uses OpenGL, right? So the computation is commands are encoded, so you call your OpenGL APIs. This generates commands which are sent over the PCI Express bus to your graphic card that is a completely isolated computational coprocessor. Will do the rendering and it will display it on screen. So this is really not much different from what happens right now. But what is interesting, for example, is that as Tom mentioned, some of our objectives in the future, in the case of CheerpX, is to actually run the full X server inside the browser. Believe it or not, this can be done. I've already done it. The prototype for that is pretty impressive. And something on top of that is to actually run also OpenGL. Now, in the case of OpenGL, we don't really want to, of course, we don't emulate the hardware, right? But what we emulate are the Linux devices. And what we need to eventually figure out, although I just have some ideas right now, not a concrete plan, is to how we encode these OpenGL commands coming from the applications to something that can directly run in WebGL. Why is this interesting? Because if you do something like that, even if the application pay the aforementioned instruction multiplier slowdown, 5x, whatever it is, the WebGL command do not. When you encode these commands, you send them to the browser, that part of the application actually run at native speed, or close to native speed, whatever is the overhead of WebGL, since you're running it effectively on the actual hardware, not anymore on this emulated virtual machine.
Okay, so basically everything is on our side in this concept. Because like I was thinking, for example, imagine like, yeah, browsers have works quite well with synchronization in this moment. Let's say I have a few devices. I have like, I don't know, some cool TV, which is like boost with like, I don't know, GeForces, and it's calculate very fast. But I'm in the same moment I have tablet on my hand. Let's say I do presentation. There's some mathematical heavy calculation, some charts. And for example, in my hand, there is some program which I don't know. I don't emulate charts on my hand, but for example, I present it to you. So you would see the emulation on the, let's say, device, as this crazy TV with GeForces, but I'm still can operate from multiple devices.
What you're talking about is called, I think, 90s computing terminology, cluster computing. So what you're doing, what you're thinking about is that you create a cluster of various heterogeneous machines, and they are somehow able to share resources. Now, this is something that exists in the literature. There are also implementation of this sort of technology. Usually, the issue with this is that the latency between running two different things is so high that you can never run applications that truly work together. You can only run applications that somehow are isolated, which in a sense defeats the whole purpose. But it is technically feasible. So you can actually, there are implementations of Linux kernel, extension of the Linux kernel, but you can also ideally make one yourself, in a sense that the idea are pretty simple, that instead of having one single machine that contains all the processes, you sort of have multiple machines that can able to move processes from one machine to the other. And this would include, for example, the graphical server, and you would be able to send a command across, not even across the network really, but across Unix sockets that are somehow wrapped over the network by this infrastructure. This is something that can be done. It could also be done in the context of CheerpX really, but cluster computing, it's something that can be impressive when you see the results, but does mean never truly convincing in terms of what you can do in practice with this solution. So I guess there is a reason why we'd rather have a single website that be accessed from multiple devices, but then there is a server-side component doing the job, because that's a much simpler approach to the problem, and in the end is effective.
Guys, I'm aware of the time. You want one more question? Okay, one small question.
What would be your dream software application that should get ported to for you? So what would be crazy, super? I don't know. For you to see ported to through WebAssembly. Like
Ported to WebAssembly natively, you mean? So using something like Chirp when we compile it from source, not something like CheerpX where we run the emulated system.
Everything that's a piece
Anything
of
that we do.
software that through.
So I really think that the industry is actually surprisingly behind the curve when it comes to what can be done with WebAssembly. So when we started Leaning Tech back in 2012, and we started with Chirp, okay, with our first product was C++. At the time was just JavaScript. Then we had the WebAssembly later on because WebAssembly did not even truly exist at the time. And what we were expecting, we would expecting, for example, that by this point, after 10 years, the AAA quality games will be directly in the browser. That you will click on the URL, you will get there, the thing will load, and you will play without having to install anything and not wait for 60 gigabytes of download from the Steam store. And this has not happened. And it has not happened for, there are some technical limitations, but to be fair, I just think that there is not yet an understanding of what the web platform can do with WebAssembly. Because, of course, if you really want to do your the best title of the year, probably the browser will be tight in terms of resources. But if you're doing a pretty decent quality game, I'm pretty sure that can be delivered on the web platform. But somehow this has not yet happened. So of course there are web games, but we still have to see major studios pushing out as the web as the main platform. I think that actually one of the reasons for that is that there is still quite an issue with exactly how you monetize them. So it's pretty obvious that you can sell things on the Steam store. So you pay with a credit card, you get you download your game, fine. Somehow I guess that how to do that in the browser is still somewhat confusing, but certainly something that I 100% believe should happen and it doesn't happen yet is demos in the browser. So there is, to this day, it doesn't happen that you have high-quality games sold on the stores, and you have a website that you can go there and simply play the demo in the browser. And there is truly no reason why this does not happen. This is technically feasible today, and it will be 100 times better than what you get right now, which is you visit the game website and you see a video of somebody else playing, which is pretty lame, really. So honestly, this is something that will be, to see our technologies being used to port very high-quality games, even just for demos purpose into the browser, that would be pretty amazing. And in terms of CheerpX, if we will get stuff like, I don't know, Blender or some even older game running under Wine, this is one of our medium-term objectives. This is a few things we like to do. Doom is DOS.
The demos, like for games and browsers, Minecraft actually used to do that for the very early versions. They actually had a playable version for inside your Chrome browser.
But was it an applet?
Yes.
It was an applet. And it's actually a recurring question for us. Why can I cannot run Minecraft using our technology? The reason is that Minecraft is not actually a pure Java application, but it uses native code to call OpenGL. And of course, again, we get to the same thing as before. We cannot run native code. We can only run Java code. Although this was true before, maybe in the future we will make some hybrid technology that uses CheerpX to run the native part of Minecraft. This is something that maybe in the future will be possible. It's not possible right now.
Thank you so much for today. I have still one question. I look right now into the audience, and I already see a couple of students that are ready for their internship. You mentioned that you want to recruit some of our students, and I was wondering, what's the current focus of Leaning Technologies? So if they would jump on board, like what sort of projects are you having in the nearby future?
Really, we have too many. We are a small company, and we do too many things at the same time. When coming to us for an internship, you can probably expect to be work on what we usually consider to be the things on the outskirts of the core technology. So the way we see our technology is that they also come in layers, really. So there is the deep, difficult compiler stuff. There is the easier optimization passes built on top of that, and there is the part of actually figuring out doing bug triaging, figuring out when somebody come to you, when a user of a customer tell you something doesn't work, to try and organize this stuff and see if it's if the user is actually right or what the problem could even be. And then there is the whole issue of writing, for example, of doing testing of this complex infrastructure. The project of Tom, for example, was to actually test CheerpX, especially when it comes to vector instructions. And you will be absolutely surprised to find out how many, although programs did work, and even Flash would work and show things on screen, we would see that there were things that will not render correctly. And when you have an application which runs several billions instructions per second, and you want to figure out which one is badly implemented, that will be a pretty bad problem. And so we did something very different. So we actually, instead of trying to find out the problem from the symptom, we went the other way around. We just asked Tom, Tom, you're going to have time. Just test every single instruction in x86, figure out what is the best way, figure out what is the best strategy to do this thing efficiently, and find out bugs. And Tom found 5 or 6 different bugs in the implementation, and we got eventually the thing fixed. And also, to a large extent, it also depends on what are your specific interests. We are a small company, so we try to accommodate also the need of people. Of course, it's something important. You cannot expect to come from day one and being able to work on the core computational part of CheerpX, just because it would be really unfair to push you there. Usually the way I reason is that I like to give you projects which are big enough to be interesting, and I expect you guys, that is something I see that you can do, to be able to work on them in a pretty much unstructured way. I tell you what I want eventually, and I let you figure out what is the best strategy to achieve that point. If some project, for any reason, needs some resources or whatever, you might have your own budget, and you might need to figure out what is the resource, what we can buy with this budget to solve the problem for us. Of course, over time, you get my attention, and we can figure out if something is actually not doable. If we need to change the direction, we can always do that.
Guys, did you note it? HR@leaningtech.com. Just saying, just in case if you didn't see it so far. Thank you so much.
And don't worry about that, because there is actually no HR person. I receive the emails.
That's the beauty of a startup. You have the CTO, founder, and HR, and everything under you.
It's,
right?
it's how it works.
Thank you so much, Alessandro. Thank you for always being in our network. You've been already for quite a while now.
It's lovely.
Yeah, actually. So if you, sorry?
Sure, absolutely, yeah. It was busy today. Today is actually half off. He deals with the kids.
We have a small little present for you. Thank you so
Victoria.
much. And hope we're going to see each other again. Let's give a round of applause, guys.
And thanks, everybody, for your time.